In this example, we're actually going to bring out this big gun, this intermediate value theorem, to actually kind of attack some of these kind of classic equations. In this example, we're going to be looking at the equation x to the fifth minus x squared minus 1 equals 0, and we're going to try to show that this equation has at least one solution. What we're going to be using in this case is actually this corollary, this consequence of this intermediate value theorem, the one where we're taking the end value to actually be 0. In this case, we're looking at this statement that if we can find 2 points, call them a and b, such that f of a and f of b have opposite signs, that is, one's going to be positive and one's going to be negative, well, we know that as long as that function you're working with is going to be one of these nice continuous functions, the only way that you can go from negative to positive is going to be crossing that x-axis somewhere. That point where you cross the x-axis is then immediately going to give you that kind of solution to your equation. In this case, it does not tell you anything about the number of solutions. That's the one downside of working with this intermediate value theorem, is it just tells me that there'll be one solution, but I might have a whole bunch. I don't know kind of the number of solutions that I have. And that's just kind of one of the annoying things you do have to kind of just be aware of. Okay, so how do we kind of dive into this thing? In this example, I'm looking at the kind of polynomial equation x to the fifth minus x squared minus 1 equals 0. And it is actually set up really nicely to use this kind of corollary of this intermediate value theorem. What I want to do is I want to identify the left-hand side of that equation with some function f. And in this example, I'm going to try to write up this solution in kind of a slightly more formal way, kind of giving a little proof of this thing. So to start this off, I'm going to let my function f of x equals that left-hand side. In this case, I'm going to have an x to the fifth minus x squared minus 1. I've identified the left-hand side of this equation to be this little polynomial. So what this polynomial equation really looks like is it looks like the equation f of x equaling 0. My goal then is going to be to find a value such that when I plug it in, it's actually going to give me this 0. What I need to do to kind of use this kind of corollary of this thing is I need to find 2 points such that my function is going to kick out 2 different kind of signs. I'm looking for a negative value and I'm looking for a positive value. Anytime you're working with one of these functions, the easiest point to plug in is a 0, and that's where I'm going to start with this thing. I'm going to have that plugging in 0 into this function. Well, 0 is pretty easy to plug in. It's going to give you a 0 to the fifth, which is 0, minus a 0 squared, which is also another 0, ultimately giving me a negative 1. We know that f of 0 is going to then, in this case, be negative. And my goal then is going to be, can I find another input that's going to give me a positive output? Well, if you tried to plug 1 into this thing, you'd have 1 to the fifth, which is 1, minus 1 squared. So you'd have 1 minus 1, and then minus another 1, giving you a negative 1. In that case, you have f of 1, which is negative 1. I have both kind of 0 and 1 kicking out negative 1. I don't see that immediate sign change happening there, so I can't use the intermediate value theorem yet. What I need to do is push the kind of x's a little bit farther. If you look at actually plugging 2 into this thing, we're actually going to kick out a positive number. So we have that f of 0 is negative, and f of 2, plugging 2 into this thing is going to be a 2 to the fifth minus 2 squared minus 1, and if you do the computation on that, it kicks out a 27, which we know is positive. So we have f of 0 is negative and f of 2 is positive. This is set up nicely. I have these 2 points where my function is changing sign. The only way to go from a negative to a positive is going to be crossing that x-axis somewhere, and that point where we cross is then going to give me my solution. To kind of kick in this intermediate value theorem, I do actually require that these functions are continuous functions. In this case, my function f is a polynomial, and these things are very nice, kind of the best case functions you can work with. So they're most certainly going to be continuous functions. So I'm going to state that since f is continuous, in this case, the reason why it's continuous is because it's a polynomial, the intermediate value theorem now gets kicked in. So I'll abbreviate this as the intermediate value theorem is going to say, so the intermediate value theorem says that, well, what does it say? Well, I know that if I have 2 points, 0 and 2, that this function switches signs. There's going to exist another point between those 2 things. So the intermediate value theorem says that there exists a real number, let's call it c, between the two kind of points in question, between 0 and 2, so that f of c equals 0. And that's exactly the statement I wanted to see. I wanted to kind of know that there was some c value so that when I plugged c into this function f, it actually kicks out a 0. What that then tells me is that this equation is going to have at least one solution. Thus, the equation x to the 5th minus x squared minus 1 equals 0 has at least one real solution. Namely, it's going to be that kind of mysterious value c. I don't know what the c is, I just know that it exists. I also don't know that there's only going to be one. I might have a couple c values in this case. In this case, I know that there's at least one solution in this thing. You can kind of see that the way that this was set up, it actually does give you kind of an idea for kind of how to find that 0. In this case, I know the 0 is between 0 and 2, but kind of as we talked about when you plugged 1 into this function, 1 also kicked out a negative 1. So you could have actually kind of rerun this argument one more time, starting from 1 to 2, and then you know that your 0 is going to be somewhere between 1 and 2. You've kind of shrunk that little window that you're looking at. And you could keep that process going over and over and over again if you keep on changing the bounds, so as long as you're keeping kind of that sign switching happening. If you kind of keep on shrinking your kind of intervals into smaller and smaller things, at some point in time you're going to be in a very, very tiny kind of window, which is going to give you a pretty accurate kind of representation of this 0. That process that I just described is what's referred to as this bisection method, and as I mentioned in kind of the last video, if you're interested in kind of looking into that a little bit farther, I do have kind of a little PDF description of how the bisection method works, as well as kind of a connection to this kind of Maple demonstration that actually has the procedure kind of coded up, and you can actually go and actually attack this thing by feeding in your favorite function f, and then it'll churn through this kind of big nasty recursive algorithm to actually kick out the 0, at least kind of up to a certain kind of margin of error.